be sure to have the handout ready when you're watching this video so that you can pause the video and work on the problems for yourself. So the classic Greek definition of a hyperbola is sort of similar to an ellipse, but instead of this, you pick two foci, but instead of, and the distance a, but instead of the sum of the distances to the foci being 2a, it's the difference. So a hyperbola is all of the points P, so that the difference of distances from the foci is equal to your constant 2a. Sort of one interesting feature of the hyperbola is as long as you're making this difference 2a, the individual distances can get very, very large. You can choose arbitrarily large distances whose difference is the same value 2a. As a result, hyperbolas sort of always shoot off to infinity in a few directions, just because you can always choose large distances that give you the appropriate difference. So that's an interesting feature that we're going to have to think about with hyperbolas. Parabolas also go off to infinity in one particular direction, but looking at this hyperbola, it seems like there are these asymptotes like this. So one of the things that we're going to have to work out once we come up with an equation for hyperbolas is what are these actually asymptotes? And if they are, what are the equations for the asymptotes? Okay, so let's pause the video now and work on number 1. See if you can figure out what the distance between the vertices of this hyperbola are, and also the distance between the foci. Okay, so up here we said we were going to call the distance from the center of the hyperbola to one focus C, so that's this distance. And we said that the difference of distances is always 2a. So here is the distance from F2 to P, and here is the distance from F1 to P. And we said that the difference of these two distances is 2a. So graphically, to subtract these two distances, I guess what we could do is, because of the symmetry of the situation, we could slide this segment over here. So that's the distance from F1 to P. We've just slid it over to the right. And then to subtract, right, we get this distance here. So we took the difference of distances and we got this distance. So this distance is 2a. But if you look at the diagram, this is actually also the distance between the vertices. So the distance between vertices is 2a. But that means the distance from the center to one of the vertices is half of that. So that's just a. So the distance from the center to one vertex is a. So that's what a really means. It's the distance from the center to a vertex. And actually, if you remember back to ellipses, that's the same as for an ellipse. So that's how we're interpreting a. It's the distance from the center to a vertex. All right, go ahead and pause the video and work on number 2. Okay, so for number 2, remember for parabolas and ellipses, we have these nice reflection properties. It seems like if there's any justice in the universe, there ought to be a nice reflection property for hyperbolas. So let's sketch what happens to rays that are emanating from focus number 1 here. Remember, the key thing about reflection is, let's see, to demonstrate this, I'm going to use this point here. The key thing about reflection is that if you sketch the tangent line, I've unfortunately obscured it, there we go. If you sketch the tangent line, the angle that the ray comes in is the same as the angle that the ray goes out. So it looks like this ray should reflect something like that going out, so that this angle going out is the same as the angle coming in. Okay, so let's do that for all of the other points on this hyperbola. So this one, the tangent line is going to be something like that. The angle coming in is the same as the angle going out. So I've drawn this tangent line a little too, not quite steep enough. So like this. So angle coming in is the same as angle going out. So it goes like this. Up here, angle coming in should be same as angle going out. So like this. Down here, angle coming in is a right angle. So going out is the same angle. So that's going to go like that. These are all going like this. And let's see. These, you can eyeball the geometry for yourself. Looks something like this. Okay, so let's see. So that's sort of generally how it looks. So I guess now we need to think about, is there some nice way to describe how this reflection is actually happening? So pause the video and think about it. Okay, so this is right the question for number 3 down here. What is the reflection property for the hyperbola? Well, if you remember to the ellipse, there were 2 foci for the ellipse, and light emanating from one was reflected towards the other. That's definitely not the case for the hyperbola, but it maybe gives us the idea that if light is emanating from one focus, we should think about the other focus when we look at the reflections. So comparing all the reflected rays to the focus f2, it looks like, well, let's see. If we back up this first reflection, it looks like if you back it up, it would go to f2. And the second reflection, it looks like it also, if you back it up, is going to f2. And same for this one. It looks like it's actually the same for all of them. So it looks like rays from F1 reflect away from F2. For an ellipse, it was towards F2, but for hyperbola, it's away. And in fact, you know, we drew this diagram as if all of these rays are reflecting off of the right-hand piece of the hyperbola. Let's do this all over again, and see how much I can actually get erased. Let's do this all over again and reflect off of the left-hand part of the hyperbola. Okay, maybe that's good enough. So if we draw a ray coming from F1 and going to the left-hand part of the hyperbola, then angle in is the same as angle out. So like this, and maybe we'll do a couple more. This ray is going to hit here. Angle in is going to be the same as angle out. So like this. Maybe this one, angle in is going to be the same as angle out. Maybe go way up here. Angle in is going to be the same as, looks like, angle out, so like this. And if you follow these reflected rays back, it looks like they also go towards the second focus. So even this one way up here. So it looks like rays emitted from one focus and reflecting off of either piece of the hyperbola are then directed away from the second focus. All right, so now we have a guess for what the reflection property of a hyperbola is. Try out this second hyperbola to see if our guess makes sense, to see if our guess still works. Okay, so what we're going to do is just sketch all the reflected rays. So for this first one down here, angle in is going to be equal to angle out, so about like that. Angle in is the same as angle out, so like this. Angle in is equal to angle out, so like that. And then our guess was these should be, these rays, reflected rays, should be directed away from focus 2. So let's back them up to see where they came from. And, you know, it's hard to draw these accurately enough, but it looks like, you know, if you permit me some inaccuracy in my drawing of angles, it looks like they are coming from focus 2. Of course, if I could draw these all perfectly, they would come exactly from focus 2.